Hi everybody. So I know there have been a lot of requests for a video tutorial on Lamella prep, and your patience has been rewarded because that is what we're going to cover here. So what you're seeing right now is an SEM image of the final result, and I'm going to take you through step by step how I got to this. So just a few basic housekeeping things to clear up before we get into the good stuff. If you haven't watched the video that I uploaded covering basic operation of the dual beam fib, unless you're already familiar with basic operation, you should watch that one first before looking at this video tutorial on Lamella prep, because we don't cover the nitty-gritty aspects of operating the fib. I will put a link in the description area so you can easily find it if you haven't already seen it. So before I go over the actual tutorial and the steps that I use to make the lamella, it's important to ask a few basic questions before you start the process of making your lamella. So when I say basic questions, that basically comes down to a couple main points. One is, what are the materials that I'm making the lamella out of, and what information am I trying to get when I perform TEM on the lamella? So for this tutorial, the specimen that I'm using is actually an integrated circuit on a silicon single crystal substrate, and specimens like this are far and wide the most commonly prepared via fib. This is something that is routinely done in the microelectronics industry. They use fib and TEM to analyze certain parts of an integrated circuit for failure analysis, for example. Now, the fact that my specimen is by and large a piece of silicon is important, because silicon has certain characteristic behaviors when I interact a gallium ion beam with it. So the general catch-all phrase for that is what's called milling behavior, and if we want to summarize what that means, essentially it boils down to how fast can I remove material and how cleanly can I remove material, or after I remove material, what does my lamella look like morphologically, or the areas I've removed material from, morphologically, what do they look like? So silicon is very nice in the sense that it removes material fairly quickly, and it also mills very cleanly and smoothly. So that's why we're going to use silicon as a demonstrating material, because it really has almost an ideal behavior in terms of its performance when we're talking about using a fib to prepare a lamella. The other main consideration when you're making the lamella is what information are you trying to get from it when you then go and perform TEM on the lamella. And obviously you want to do this, think this through, figure it out before you get to the fib, because what you do in the fib is definitely dictated by what your end result in the TEM or the end information you're trying to get in the TEM is supposed to be. So in the case that I'm using here for the tutorial, I actually have on the integrated circuit device, there's an area with a film on it, and my goal in making the lamella is to analyze this thin film. And so this thin film is nanoscale, so tens of nanometers in terms of its thickness. And so that's my primary interest when I'm making this lamella, is that film on the surface of the substrate. And so the reason this is important is that I always have to keep in mind when I'm making the lamella that the area I care about, when I do the TEM, is basically right at the surface of the specimen. I don't really care about what's happening 2 or 3 microns down from the surface into the bulk. I only care about really right at the surface what's going on. So another scenario to consider is that maybe you're not really interested in the surface. Maybe you're interested in the bulk microstructure of your material. Now, obviously, if we have a single crystal substrate like we do here, that's really sort of irrelevant. But if you're dealing with, say, a polycrystalline specimen, then that may be something that's more important and more relevant to consider. Generally, with a single crystal, it's not relevant. Generally, in that case, you are considering the near surface region. But for people who do work on polycrystalline materials, then going into the bulk tends to be more relevant. And the last thing to consider also is, what kind of specimen quality do I need? So the golden rule with TEM, of course, is that thinner is always better. But depending on your type of analysis, getting the sample as thin as you can possibly get it may not be necessary and may actually be counterproductive. So in the scenario we're looking at here, the idea that we want to get it as thin as we possibly can at the area that we want to analyze is definitely true, because we're talking about analyzing a thin film on the surface of a substrate. And when we do that, we're typically talking about using techniques like high-resolution imaging or atomic resolution STEM imaging. And for scenarios like those, you do want a really, really thin, high-quality specimen. But that may not always be the case. So one thing to consider is, what if your goal of doing the analysis, for example, is to do weak beam dark field imaging? Well, weak beam dark field imaging is kind of interesting in the sense that if the sample's too thin, it actually becomes somewhat counterproductive to do weak beam dark field imaging. So you always have to start by asking the question, what am I trying to learn by doing TEM? So generally speaking, yes, you're trying to get the sample as thin as possible, but again, maybe, maybe not, depending on the analysis that you are trying to do. In the scenario that I'm using here for the tutorial, of course, because it's a thin film on a substrate, then yes, we are trying to get the sample as thin as we can in the near surface region, because ultimately we would want to do high resolution imaging or atomic resolution imaging. So I know I've done a lot of talking to this point and we haven't even started the tutorial, and I apologize for that, but I did want to get through a few disclaimers first. And I do want to go over just a few other points about the tutorial so you kind of know what to expect. So the tutorial doesn't cover basic operational elements of using the fib. Again, if you're not familiar with those, please look at the video that I'm going to put in the description box. And the other thing to keep in mind too is that the video I recorded was one continuous shot and it took close to 80 minutes. So what I did to condense that down was I sped up the video. So the baseline speed up factor I used for the whole video was 2x, and then there were portions that I sped up more to 4x, 8x, and I think there was even a couple spots where I did 12x to kind of condense things to get this video into a somewhat manageable length, or a length that is a little more conducive to effective, meaningful watching. And so without further ado, we will go to the video and I will start showing you my tutorial for making a lamella. Alright, so beams are on, platinum is hot, ion source is on. I unpaused my electron beam. I'm navigating to an area of interest. My electron beam settings right now are 3 kilovolts and 5.5 nanoamps, which I'm going to use eventually to put down electron beam platinum. So right now I'm navigating around. I'm going to make a lamella inside one of these square pads that you're seeing in the E-beam quad. I'm going to align the pad so those features are square in the image, because those are actually cleave directions for the substrate that I want to use for imaging when I prepare the lamella and eventually I put it into the TEM. So now I'm setting eccentric height. So I focused and linked the working distance, and now I'm tilting. I see the image shift from the middle, my feature of interest rather. Then I'm using the Z control of the stage to bring it back. And again, I'm going to do this iteratively. You can see that the contrast in the image changes as the stage is tilted. So feel free to perform auto contrast and brightness as needed. The hotkey for that on the keyboard is usually F9. So you can see it's getting really bright, so you could have done auto contrast, although I didn't do it here because I knew I was going to tilt back to 0 anyway to do the E-beam deposition. And so now I'm back to 0, and I'm going to do the alignment. So I'm doing the gun alignment, and now I'm doing the lens alignment. So adjusting those crosshairs until the image shifting is minimized. Again, this is strongly dependent on your beam voltage and your beam current. And now I'm adjusting the stigmators to get the sharpest image possible. And so E-beam alignment is now done. Go ahead and get a good focus. And now I'm going to make the lamella right in the middle of that pad. So now I'm going to draw a rectangle pattern inside the pad that I'm going to define for E-beam platinum deposition. I'm using dimensions of 10 and 1 for X and Y respectively. And I'm using an input value of 3 for the Z, although I don't usually get that much thickness when you actually do it, but that's what it's indicated as. And now the video is sped up. And it's done now. So unpause the image, you can delete that pattern, retract the platinum, and now I'm going to tilt to 52 degrees for I-beam platinum deposition. So it moved a little bit from center, so again I can adjust that with the stage Z. Now I'm activating the I-beam quad, so I'm at 30 kilovolts and 0.3 nanoamps. You can go live and then use the shift knobs to center the strip in the image. And now we're going to define a rectangle pattern and deposit platinum using the I-beam. So the X and Y dimensions are a little bigger than I used for the E-beam. So the X is now 12 and the Y is 1.5 microns and the Z is 3. And it's important when you're doing I-beam platinum deposition that you have a optimal current density when you're doing that. Because otherwise your deposition will be either excessively slow and inefficient, or you won't end up with deposition, you'll end up milling. So the video is being sped up here because this process is actually quite long. This is about a 6-minute step. So I-beam platinum deposition is done. So now I'm going to retract the platinum GIS, tilt to 57 degrees, and I changed my ion beam current to 7 nanoamps to cut trenches. So for this, I'm going to use the regular cross-section with a rotation of 180 degrees, which you can do in the Advanced tab. And so you want to use silicon for your application file. That's the general milling file. I think the X and Y dimensions for this were 16 and 5, and then the Z was 3, but really in silicon it ends up cutting more like about 7 or 8 when you input 3, so it's a little bit skewed. Obviously, if you were doing this with a softer material or a harder material, then you would cut deeper or shallower respectively. So now I tilted 5 degrees the other way to 47 degrees, and I rotated the pattern 180 degrees, and I executed the same pattern but from the bottom. So the reason for tilting plus or minus 5 degrees is it tapers the lamella from the top down and helps preserve the platinum. And again, remember, the goal of this sample is we're trying to look at that very, very near surface region of the material. So we really want to preserve the protection as much as we can. So I'm tilting back to 57. I drop my ion beam current now to 3 nanoamps. And I'm going to keep the same pattern, but rotate it 180 back to the top. I'm going to change the dimensions a little to make it smaller. I reduce the Z because we're milling a sidewall and the sputtering yield goes up. So we'll go ahead and speed this section up a little bit. You can see here I'm also using live electron beam imaging while milling, and I'm also using averaging. That's especially helpful when your ion beam current is high relative to your E-beam current. Now I'm tilting to 47 degrees, so 5 degrees the other way off from normal, rotating the pattern back to 0 degrees, and then executing basically the same pattern. I made a slight change to the dimension, the Y dimension, I should say. And so once this is done, we will now move to undercutting the lamella. So for that, I'm tilting to 7 degrees, and I changed my ion beam current down to 1 nanoamp. So once it's at 7 degrees, I can go live, and you can see the lamella isn't centered anymore. So I'm using the shift knobs on the MUI to recenter it, and now I'm drawing 3 rectangles in a lopsided U, or what some people refer to as a J cut. I changed the pattern order to what's called parallel, meaning all 3 are executed at once. And so the idea now is you're cutting around the lamella and you're leaving only a really small part attached to the actual substrate or the bulk. And so it's really pretty easy to see when you've cut through your defined areas using the live ion beam signal from the area that you're milling. Again, you may need to manually adjust your contrast brightness to see it better. Okay, so I stopped it, and now I'm tilting back to 57 degrees, and there's one more step we're going to perform before doing the lift out procedure. So once I get back to 57 degrees, I can shift the image back with the shift knobs, and now I'm using a cleaning cross section with a rotation of 180 because I'm performing this pattern on the top side of the lamella. So you can see there's actually a little bit of bowed out area, which typically happens after you do the undercut. And so this is just to clean that off. And you can also see that the lamella is not quite perfectly level in the ion beam image. So I'm actually adjusting the scan rotation of the ion beam image very slightly away from 180 degrees just to kind of square it up. And then I can execute the pattern. And in the electron beam image, we can actually see the side of the lamella as the cleaning cut is being performed. All right, so the cleaning cut is done. And so now we can do the lift out. So the first thing I did was I turned off averaging for the E-beam, and then I tilted back to 0 degrees for the stage. I dropped my ion beam current to 30 picoamps. You can see now my ion beam image again needs to be shifted back, and again I'm making a fine tweak to the scan rotation just to square the lamella up in the ion beam image. I inserted my platinum and my omniprobe, and now I'm going to approach the omniprobe to the lamella. So it's coming in from the left side of the electron beam image, and because of the scan rotation set to 180 for the ion beam, it's actually going to come in from the right side of the ion beam image. And so now I have to move the omniprobe down, and this is where the dual beam capability of the fib is important, because otherwise you really wouldn't be able to position the omniprobe tip. So I also have a pattern here in the I-beam quad that's a rectangle defined for I-beam platinum deposition. So I'm positioning that omniprobe right there at the free edge of the lamella. I resize the box, and then I start depositing platinum. And so you can see this actually happen in the E-beam image, the buildup at the point of contact between the omniprobe and the lamella. And so you can run this until you get enough of a buildup and then stop. So once you have a good weld there, and again, you can kind of just go by feel, you can cut the last point of contact between the lamella and the bulk free. So I increased my ion beam current to 0.5 nanoamps, and I kept the rectangle, but I changed the application to silicon. And so I moved it around the contact point, and now you can see in the E-beam image, once it's been freed, the lamella just kind of flicks off and moves. And now I can separate the lamella from the bulk by moving the stage down, and then I can retract the platinum and retract the omniprobe. And so once the omniprobe has been retracted, I can navigate over to the grid, and we can set that up for attaching the lamella. So now I've moved over to the TEM grid holder, and I'm going to look for the clip that has the grid in it, which is this one, and I'm now going to set the grid up to be ready for lamella attachment. So focus on it, link Z with the working distance, and then you can see the grid is rotated, so I'm going to rotate the stage to align it, and then I'm going to set eccentric height in the middle of the post, which has a little bit of a notch in it. There are different places that people attach lamellas. I prefer to attach them in the middle. Some people will attach them on the sides, but I prefer to do it this way. I'll get into that in greater detail a little bit later. So you can also see that the grid isn't perfectly edge-on, so I'm going to do a manual adjustment of the tilt until it's perfectly aligned, and I'm looking straight on edge. And so that was about minus 0.7 degrees. And now I'm inserting the platinum GIS and the omniprobe. So to facilitate easier lamella attachment, one thing I like to do is to cut a shelf into the middle of the post. And so for this, I'm using a fairly high current. This is 15 nanoamps and just a rectangle pattern. This is about 20 microns wide. And I'm using the live ion beam image to see my progress, or I should say the live ion beam signal from the area that's being milled to see the progress. And so this is going to make it easier to attach the lamella because I have this nice flat shelf in the post. So now that the shelf has been cut, I reduced the ion beam current to 30 picoamps, and now I'm using E-beam and I-beam imaging to position the lamella at the edge of the shelf for attachment. You want to make sure when you attach the lamella to the shelf that you do it right at the edge of the shelf that is closest to the middle of the post. Otherwise, you're going to end up with part of the shelf blocking the lamella when you do TEM, and you obviously don't want that. So you don't have to have the lamella in contact with the shelf. It can be really close, but not perfectly in contact, but we actually do have light contact here. So I have a rectangle pattern allotted for I-beam deposition, and I'm just drawing a small square, and I'm going to weld one corner to the shelf. And again, you're just going by feel here until you get a little bit of a buildup. And once you have that corner completed, you can stop the weld and move the box over to the other corner and repeat. So the advantage of mounting the lamellas like this is because you have them fixed on both sides, they're less prone to warping and deformation when they get really thin, as opposed to some other methods where they just attach the lamella on one side and then they thin it. You can end up with the lamella curling or bending in on itself, and that obviously can make it harder to image in the TEM. So doing this just provides more mechanical stability. Okay, so we have our welds done, and now we need to cut the omniprobe free. So I changed my pattern to silicon and my ion beam current to 1 nanoamp, and I just positioned it over the edge of the omniprobe and executed the pattern. And I can see now my omniprobe is free. Then I moved back to 30 picoamps. I again separated the lamella from the omniprobe by moving the stage down, and then I can remove the omniprobe and the platinum GIS. So we're getting now to doing the final thinning. And so when you're electron beam imaging while final thinning, you want to use a much lower electron beam current. I reduced it from 5.5 nanoamps to 0.17 nanoamps. And the reason you want to do that is you're going to get less contamination buildup on your sample by using a lower electron beam current than you would with a higher one, and you obviously don't want contamination on your lamella when you're TEM imaging it. And so again, I changed the beam settings, so I have to realign everything. So I did the gun alignment and the lens alignment, and now I'm doing the stigmation to get the nicest, sharpest electron beam image that I can. And now I'm going to do a fine adjustment to make sure the lamella is accurately at eccentric height. And once I'm done with that, I'm going to tilt the stage so the lamella is at normal incidence to the ion beam. So keep in mind, because we tilted minus 0.7 degrees to align the grid, normal incidence now is actually 51.3 degrees to get normal incidence for the ion beam. And so that's important. You want to keep that in mind when you're doing your final thinning steps. Samples at eccentric height. So I can go to my live ion beam image and I can shift the image so it's coincident with the E-beam. Now I'm going to go up to 0.5 nanoamps. I'm going to tilt plus 1 degree from normal incidence, and I'm going to now use a cleaning cross section on the upper side of the lamella. And so you want to make this a couple hundred nanometers in the Y dimension. With the X, I'm starting with 10 microns, and the Z is about 2. And so this is going to be most of the final thinning with the cleaning cross-section pattern. And we can actually see that side of the lamella being thinned in the electron beam image. This is sped up a little bit. Once this is done, I'm going to tilt minus 1 degree away from incidence. I'm going to drop my ion beam current down to 0.3 nanoamps. Rotate the pattern so it's 0 degrees. It was previously 180. I don't think I mentioned that, but it's now 0 degrees. I'm going to execute it from the bottom, and I'm actually going to drop the X dimension down a micron to a micron and a half. So this produces a series now of staggered cuts into the lamella, if you will, which empirically helps to keep it more mechanically stable than if I keep that X dimension the same, and it also saves time. It will result in a little bit less usable area than you might otherwise get, but in TEM your sampling is terrible anyway, so that's really not something that should be a huge consideration. And so once this pattern is done, I'm going to drop the current down again to now 100 picoamps, tilt 1 degree away from normal incidence, plus 1 degree I should say, reduce the X dimension again, rotate 180, and now I'm going from the top side of the lamella. And so again, it's another staggered cut. And so you can see this in the E-beam image now, the new area that's being cut. You can kind of see it's kind of like a window inside of the previous cut on that side. So each cut moves in a little bit more than the previous one, and again, that's for mechanical integrity. And once this pattern is done, I'm going to tilt minus 1 degree from normal incidence, drop my beam current down again, this time to 50 picoamps, and once again, I'm going to rotate the cleaning cross-section now to 0 degrees. I'm going to bring the X dimension in a little bit to again stagger the cuts and execute this pattern from the bottom of the lamella. And it's a little tougher to see because now we're milling the side of the lamella we can't see in the E-beam. But as the lamella gets thinner, you can start to see the millings that you're doing from the non-visible side in the E-beam, although we really can't see that yet here. But it will become more evident as the lamella gets thinner. And once this step is done, the ion beam voltage will be reduced to 5 kilovolts for the next 2 milling steps to reduce the damage layer to the specimen. So I reduced it to 5 keV and I went to 48 picoamps. And now I'm tilting plus 2 degrees away from normal incidence. I'm going to keep the cleaning cross-section pattern, but again I'm going to stagger it just like previously. So I'm going to bring that X dimension in, and I think the Y dimension is going to be changed just a little bit. Again, rotate 180 because we're coming from the top. And one thing you may notice when you drop the ion beam voltage is that there's some drift in the image as a result of the voltage change, and that takes a little bit of time to settle down. And so I actually made a little bit of a mistake here in that I didn't wait for that to settle before I started doing my milling. So this step actually was a little bit more aggressive than I would have liked, but it still ends up with a usable sample. But you'll see I actually stopped this pattern prematurely to prevent overmilling of this side of the lamella. So again, you always have the option to do that. Don't think that you have to always run a pattern to completion. If something's going wrong, you can stop it. And so I'm about to do that right there. So now I will tilt -2 degrees away from normal incidence. Keep the same pattern, but again, stagger it. So I'm going to bring the X dimension in a little bit, rotate 0 degrees, because now I'm coming from the bottom. And I'm going to wait a little bit here to make sure that the drift has settled down. It should go away pretty quick, but you need to be patient and then go ahead and start the pattern. So now again, we're milling the side that we can't see directly with the E-beam, but we might be able to see now because we're cutting again a staggered pattern into the other side. We might be able to see that window here as the sample gets thin. So my platinum's starting to get thinner, which is good. Although we don't want it to go all the way away yet because we still have more milling steps to do at 2 kilovolts. So we're going to stop this now. The ion beam voltage is going to be reduced to 2 kilovolts. And now I'm tilting +4 degrees away from normal incidence. And I'm going to realign the ion beam with the direct alignments. I think the beam current here is 27 picoamps. So you're going to notice your ion beam image is really, really bad at 2 kilovolts. That's about what you expect because your beam voltage is low and your ion wavelength is therefore very large. And so we've been using cleaning cross-section, but now we're going to go back to the rectangle. So I'm going to move the X dimension in a little bit from what it was previously. The rotation doesn't matter anymore because it's a rectangle. And I'm going to put it over that top side of the lamella. Remember, the goal of this sample is to look at the very near surface region, so I want to be very careful that I don't overmill it. So one trick that I use is to draw a rectangle pattern in the E-beam image and then use a scan rotation of the E-beam to align the surface perfectly left to right, and then I can position that pattern right at the wafer surface and use that as a clear indicator that I still have my surface present. So now I'm going to tilt -4 degrees away from normal incidence, move the X dimension of the pattern in a little bit again, and execute one last milling step from the bottom side of the lamella, which again is the opposite side that we're seeing in the E-beam. And then once that's positioned, I'll go ahead and start the pattern, take a snapshot, and then make sure the image is stable, and go ahead and execute. You want to be really careful here, especially with your last steps. So I went ahead and started it. Okay, there's my indicator box again. So I still have stuff above that top yellow line. So I basically want to keep going until I have just a little bit of stuff above that top line, because then I know that I've made it as thin as I can while not getting rid of the surface. And so right about there. So the lamella is now done. You definitely do not want to do any more ion beam imaging at this point because you're going to end up damaging your sample. And you don't want to do really any more e-beam imaging either, although I'm going to go ahead and take a photo here so you can see again the final result, which I showed you already previously. And I'm going to go ahead and mag in here and take another photo so you can more clearly see that near surface region and that film that we're interested in imaging. And so you can see very clearly that really thin, bright layer at the surface is still intact, and I have just a little bit of protective platinum still on top of it. And that's exactly what you want when you're making a lamella, where you're trying to preserve that very, very near surface region. And so at this point, you don't want to do any more imaging of the specimen in the fib. You want to turn everything off, take the sample out of the fib, and go straight to the TEM, if possible. So one of the most commonly asked questions is, how thick is the lamella? And that is a really difficult question to ask, because you have to keep in mind your lamella is A, not uniform in thickness, and B, also probably has some deformation or bending to it. And of course, you also have to keep in mind that you're concerned about the thickness really at only the areas that you're interested in performing TEM on. That being said, one method you can use to get a rough idea of your lamella thickness is to tilt back to normal incidence for the electron beam and then measure the thickness edge on. Again, keeping in mind that the lamella is tapered, and also keeping in mind the possibility that you may have parts of the lamella where you have abrupt changes in thickness. So one of the things that happened with this lamella when I did the first 5 keV step, because it was a little bit too aggressive, because I didn't wait for the image instability to calm down, was I ended up with a little bit of a discontinuity in the cross-section face as a result of that step. So when I view the lamella edge on, you can see I have that distinct dark line in the middle, which would be the top of the lamella, but you can see I have a little bit more material on the upper side as opposed to the bottom side. And again, the presence of any of those discontinuities may not even be important. It's not important in this case because we're interested in imaging the very near surface region of the specimen. So what is the thickness of the near surface region of the specimen? Again, it's not necessarily straightforward to do that, but again, if we want to get a rough idea, we again use that dark line as the reference for the top of the lamella, and we can see as we move outward from that, we have two somewhat abrupt changes in contrast on either side of it, sort of where you have these bright lines that end, or again, you have abrupt transitions. So making a measurement here, we get about 25 nanometers. And that's one method that you can use to get a rough idea of your lamella thickness. If you wanted a more accurate measurement of the area you're analyzing in the TEM, you would actually need to use techniques that are specific to the TEM, which obviously can only be performed while you're performing the TEM. So that concludes the lamella prep tutorial. So thank you for your patience. I know this was highly requested, and I'm glad I finally got around to it, and hopefully I did it justice. If you have any questions, please feel free to leave them in the comments section below. Please like, share, and subscribe. And as always, if you have any suggestions for future video topics, please feel free to let me know.